Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is battery discharge characteristics. Our objective today is to discuss battery discharge characteristics. We'll examine voltage regulation, discharge curves, and discuss factors that influence battery capacity. This lecture operates under the presumption that you're at least marginally skilled in basic DC circuit analysis, specifically basic series circuits. If you need to brush up on these skills, by all means check out the Basic Electronics 1 DC Circuit Analysis playlist available at the Big Bad Tech channel. Additionally, this is meant to be a follow-up to the Introduction to Batteries lecture, also available at the Big Bad Tech channel. If you haven't watched this lecture yet, by all means please take the time to do so now. A brief disclaimer before we begin. Always consult the manufacturer's datasheet for the particular battery of interest. This lecture primarily deals with lead-acid batteries, and different chemistries necessitate different analysis techniques. Do not assume for a moment the specifications presented herein are universal in nature. Batteries can explode into a ball of white-hot fire or otherwise be damaged and rendered useless if you charge or discharge them incorrectly. A battery is an energy storage device and as such represents stored hazardous energy if it is not properly locked out and tagged out. A short circuit across the terminals of a battery, be it from a conductive tool or an errant wire that bridges the terminals, can produce a high current and damage the battery. Take necessary precautions when working around or with batteries. Let us begin. Recall during the Introduction to Batteries lecture, we briefly discussed the discharge process, nominal voltage, nominal capacity, discharge rates, and introduced C ratings. I'd like to briefly revisit these topics and continue to discuss them in greater detail. A battery is an electrochemical energy storage device that, when discharging, converts chemical energy into moving electrical charges. The discharge process exhausts the chemically active materials, in such time the reaction slows down and eventually ceases. In a perfect world, a 12-volt battery would provide a constant current at a constant 12 volts for a predetermined length of time, and then simply drop off and cease to function. This is essentially the logic behind the amp-hour capacity rating of a battery. It basically ignores voltage variation of the battery, and a user is left to assume a nominal value. Additionally, the amp-hour rating of a battery is a single snapshot of, as we'll soon learn, a moving target and can vary widely due to a number of influencing factors. Again, in a perfect world, a 12-volt battery with a 24 amp-hour capacity could theoretically deliver 24 amps for 1 hour, 12 amps for 2 hours, 8 amps for 3 hours, 6 amps for 4 hours, 4 amps for 6 hours, 3 amps for 8 hours, 1 amp for 24 hours, or any other combination of amps and hours that equals 24 amp hours, the whole time maintaining a flat line of 12 volts. This is a simplification only, and real batteries don't exhibit this behavior. The first brick wall reality throws in the way of this simplification is that batteries exhibit an internal resistance, sometimes called ESR or equivalent series resistance. The internal resistance comes from two sources. One, the relatively constant electrical resistance, and two, the varying ionic resistance, which is a function of electrolyte mobility and functional surface area. The internal resistance is a simplification of these effects into a single resistor in series with the battery and any electrical load attached to its accessible terminals. For the purposes of this lecture, we'll assume the internal resistance is constant, but be aware, the varying ionic resistance changes at the extreme limits of discharge. Those with an understanding of basic series properties can already see how an additional resistor in series with our electrical load can change the observable electrical properties for varying load conditions. In a perfect world, a battery has no internal resistance. In this case, a 48 ohm resistor will draw 250 milliamperes from a 12-volt source and experience a 12-volt drop. Similarly, a 0.5 ohm resistor will draw 24 amps from a 12-volt source and experience a 12-volt drop. In the real world, however, the internal resistance of the battery is placed in series with the electrical load. In open circuit conditions, in which no current flows, no voltage is dropped across the internal resistance of the battery, and all 12 volts is dropped across the open. Ideally, in no load conditions, no chemical reactions occur, and the battery can stay charged indefinitely. Though, as we learned in our previous lecture, this isn't really the case, and we can expect a measurable amount of self-discharge over time. When an electrical load is connected to the battery, the internal resistance and the electrical load are placed in series with one another. The 12-volt source sees not just the resistance of the electrical load, but rather the resistance of the internal resistance in series with the electrical load. Resistance in series adds up. If the resistance increases, current decreases. Being a series circuit, it can be said that current through the internal resistance and the electrical load is the same. Given current travels through the internal resistance, there will be a voltage drop across it. Given our understanding of Kirchhoff's voltage law, what goes up must come down, it can be said that the voltage rise will equal the summation of voltage drops. What this all means is that not only will current be lower because of the internal resistance in series, observed voltage at the accessible terminals of the battery will be less than the ideal 12 volts when the load is actually drawing current. Given that both voltage and current decreased, power delivered to the load will proportionately suffer. Power dissipated by the internal resistor is essentially written off as a loss. The observed voltage at the terminals of a battery when it is delivering current is often known as the working voltage of a battery. As we'll learn, the observed working voltage is different than open circuit voltage and dependent upon the current drawn by the electrical load. Consider a 12-volt battery with 100 milliohms or 0.1 ohms of internal resistance. In open circuit conditions, a voltmeter would still measure an open circuit voltage of 12 volts across the accessible terminals of the battery. If, however, a 48 ohm electrical load is connected to the battery would see 48 plus 0.1 or 48.1 ohms of total resistance. Accounting for internal resistance ever so slightly increased total resistance, but not excessively. Ohm's law states that source current is equal to source voltage divided by total resistance. Substituting in the necessary values, we find only roughly 249.5 milliamperes of current travels through this series circuit. In comparison to our expected value of 250 milliamperes during ideal conditions when there is no internal resistance, it's not that marked of a change. A 48 ohm resistor experiencing 249.5 milliamperes of current will experience an approximately 11.975 volt drop, essentially 12 volts. The effects of the internal resistance are only noticeable during periods of excessive current draw. Consider a 0.5 ohm electrical load connected to the battery. In this case, the source would see 0.1 plus 0.5 or 0.6 ohms of total resistance. Accounting for internal resistance made total resistance increase, only this time the 0.1 ohm internal resistance in proportion to the 0.5 ohm load resistor increased at a much greater amount. Ohm's law states that source current is equal to source voltage divided by total resistance. Substituting in the necessary values, we find only 20 amps of current travels through this series circuit. In comparison to our expected value of 24 amps during ideal conditions, when there is no internal resistance, it's a substantial change. A 0.5 ohm resistor experiencing 20 amps of current will experience only a 10 volt drop, the other 2 volts being dropped across the internal resistance of the battery. This is to suggest that the working voltage observed at the accessible terminals of the battery will decrease during periods of excessive current draw. The greater the internal resistance and the greater the current draw, the more observable these effects become. Power is lost to the internal resistance of the battery and unavailable to the electrical load. The voltage regulation curve for a battery is a plot of the battery's working voltage as a function of current draw. For a relatively new, fully charged, 12-volt, 7 amp hour battery being asked to supply 140 milliamperes, the working voltage is approximately 12.89 volts. However, when asked to supply 100 times this amount of current at 14 amps, the working voltage drops to 11.03 volts. The internal resistance of this battery can be estimated using several different techniques at specific points on the curve. But if you want the big picture, the easiest method might be to insert a trend line and determine the absolute value of the slope. Given Ohm's law states that resistance equals voltage divided by current, that's what resistance essentially is. In this case, the relatively new 12-volt 7 amp hour battery has an internal resistance of approximately 123 milliohms. If you wanted a quick and dirty method of determining an approximate value of internal resistance of this battery, we could take the two extremes of our curve and essentially do the same thing. At a current draw of 140 milliamperes, we observe 12.89 volts, and at 14 amps, we observe 11.03 volts. This formula suggests the internal resistance is slightly higher at 132 milliohms because of the steeper slope between the two extreme endpoints. This being said, it's not far from what the trend line suggests. Additionally, one could take two proximal data points and determine the slope between them, or resort to calculus to find increasingly accurate representations of internal resistance at that particular moment. Regardless of the method used, one would find an internal resistance of approximately 123 milliohms, which is good enough for our purposes. Internal resistance, among other things like temperature and discharge period, is subject to change with the age and condition of the battery. Consider the voltage regulation curve for three different 12-volt 7 amp hour batteries of varying age. Battery A is relatively new. Battery B is past retirement age, and Battery C has both feet in the grave after suffering a lifetime of heavy use, abuse, and neglect. This battery is a manky old goat that's been fed nothing but the bitterest of acorns its whole life and then cooked far too long. When viewed from a distance, the voltage regulation of these three batteries may not seem so bad. However, when we zoom in on the curve, we see that when compelled to supply 14 amps of current, Battery C's output voltage drops to only approximately 8.41 volts. This is to suggest that the internal resistance of Battery C is much greater than that of Battery A or Battery B, and more voltage is being dropped across the internal resistance when asked to supply such a large amount of current. Trend lines of Battery B and Battery C indicate these batteries respectively have approximately 177 milliohms and 270 milliohms of internal resistance. We'll return to discuss endurance and energy in a moment, but right now consider the instantaneous power capable of being delivered by these three different batteries. At the extreme right of the voltage regulation curve, all three batteries are being compelled to deliver 14 amps of current. However, the working voltage available to the electrical load is substantially different because each battery has a different internal resistance. The voltage across the electrical load is approximately 11.03 volts for Battery A when it delivers 14 amps. Therefore, Battery A is delivering approximately 154.4 watts of power to the electrical load. The voltage across the electrical load is approximately 10.09 volts for Battery B when it delivers 14 amps. Therefore, Battery B is delivering approximately 141.3 watts of power to the electrical load. The voltage across the electrical load is only approximately 8.41 volts for Battery C when it delivers 14 amps. Therefore, Battery C is delivering only approximately 117.7 watts of power to the electrical load. At a dead sprint, Battery C does not have the instantaneous power output of Battery A or B. If power is energy over time, it stands to conjecture that energy is power times time. Given that the instantaneous power output of Battery C is less than that of Battery A and B, it would not be a surprise that over the course of the same length of time, Battery C would deliver a smaller amount of energy. Battery A and B will quickly outpace Battery C because they deliver more energy per second. Power is energy over time. This is entirely neglecting the fact that such a worn-out old battery might not even make it across the finish line if the finish line is a considerable distance away. One can consider the power dissipated by the internal resistance as a loss to the system. With an increasing loss at increased discharge rates, one can expect a battery to exhaust itself quicker. This is a perfect transition into our next topic regarding battery discharge characteristics and energy capacity at different discharge rates. Recall, during the introduction of batteries lecture, we discussed amp hours, watt hours, nominal capacity, and I introduced a rather slippery specification called the C rating of a battery that lends itself to misrepresentation and misinterpretation. We'll review these topics and discuss additional dirty details regarding battery capacity. First, let's review the basics. At a basic level, energy can be visualized as a quantity of gasoline in a tank. If you wish to travel a great distance, you need a tank full of gas, and you need to use it efficiently by keeping losses to a minimum. Power, in contrast, is the time rate withdrawal of gas from the tank. If you've got a given quantity of gas in your tank, and you go up a steep hill at a quick speed, you'll consume more gas per second and empty your tank quicker than if you traveled a reasonable speed on a flat road. Energy is ordinarily measured in units of foot-pounds force, or joules, where a joule is a newton of force expressed for a distance of a meter. Power, in contrast, is measured in units of foot-pounds force per second, or watts, where 1 watt is 1 joule per second. Power is a unit of energy, the joule, per unit of time, the second. Power is energy over time. It stands to conjecture that energy is power times time. If during the course of increased power withdrawal, an increased amount of power is lost, one would expect a given quantity of energy to be exhausted quicker. Battery capacity is ordinarily determined using 4 different methods: constant current, resistive load, constant power, and pulsed current mode. The one we'll be talking about today, and the most common specification used, is constant current mode, where a battery is subjected to a load that draws a constant current for a measurable quantity of time until the battery reaches a predetermined cutoff voltage, any further discharge beyond which may permanently damage the battery. The cutoff voltage is essentially when a battery taps out and says, "I yield." If a battery delivering power at a certain rate stays in the fight longer, it delivers more energy. Energy is power times time. This is essentially the logic behind the amp hour capacity rating of a battery. It basically ignores voltage variation of the battery, and a user is left to assume a nominal value. As previously demonstrated though, increased current draw will ordinarily reduce the working voltage of a battery, so the nominal capacity of a battery in units of amp hours can be viewed as a single snapshot of a moving target. In a perfect world, a 12-volt battery with a 24 amp hour capacity should be able to provide 24 amps for 1 hour, 12 amps for 2 hours, 8 amps for 3 hours, 6 amps for 4 hours, 4 amps for 6 hours, 3 amps for 8 hours, 2 amps for 12 hours, 1 amp for 24 hours, or any other combination of amps and hours that equals 24 amp hours, the whole time maintaining a flat line of 12 volts. This isn't really the case because not only does the rate of discharge affect the working voltage and power output due to losses across the internal resistance, voltage output also noticeably dips as a battery reaches the end of its capacity. These observed effects shouldn't come as a surprise. Those that have trained for an athletic event are no doubt aware that a weekly regimen of hour-long training sessions have nowhere near the intensity of a 5-minute fight. It would be expected that a 24 amp hour battery being asked to supply 24 amps at a dead sprint wouldn't last the full hour. Additionally, as the battery reaches the limits of its capacity, the electrochemical reaction central to the process could be expected to slow down as active material and functional surface area is consumed. Capacity is largely determined by the type and amount of active material. All other considerations being equal, physically larger batteries have larger capacity. Consider 3 batteries with the following nominal capacities: 7 amp hours, 24 amp hours, and 230 amp hours. Realize, however, we're not exactly comparing apples to apples, because the 2 VRLA batteries in the front are 12-volt batteries, and the FLA in the back is a 6-volt battery. This means in a perfect world, the small battery has 84 watt-hours, the middle battery has 288 watt-hours, and the large battery in the back has 1,380 watt-hours, or 1.38 kilowatt-hours. This is again a simplification and a single snapshot of a moving target. The C rating of a battery is undoubtedly the slipperiest of specifications, and misrepresentation and misinterpretation of capacity can occur if used improperly. The C rating of a battery is a means of relating energy capacity to the rate of discharge. Additionally, the C rating of a battery is used to convey discharge and charge rates and convey maximum safe discharge rates. As previously discussed, the real observable energy capacity of a battery is dependent upon the rate of discharge, and a battery cannot be expected to deliver the same amount at a dead sprint when the electrical load is chugging current in great quantities, in comparison to a leisurely stroll when current is casually sipped by the load. It is for this reason most batteries' nominal energy capacity in units of amp hours is expressed at the same rate, placing every battery on the same playing field, though as we'll soon learn, this isn't always the case. A C20 rating is the capacity of the battery in amp hours as if it delivered constant current for a period of 20 hours. A battery with a C20 capacity rating of 24 amp hours means this battery delivered not 24 amps for 20 hours, but rather 1.2 amps every hour for a period of 20 hours, or 24 amp hours, until the electrical chemical reaction central to the conversion process is exhausted and the battery reached a predetermined cutoff voltage. This C rating in effect establishes a predetermined length of time, a constant current, and a firm cutoff to level the playing field. The misinterpretation of C rating values comes from two sources. First, one must inspect the datasheet of a particular battery to determine the cutoff voltage and which C rating the nominal energy capacity is meant to represent. Again, the nominal capacity of a battery is a snapshot for a particular discharge period or C rating. Ordinarily, most nominal battery capacities are rated at the C20 rating. However, batteries central to off-grid storage are often rated at the C100 rating, meaning the nominal capacity is determined over a longer period of 100 hours. Current draw for the lengthier C100 rating is proportionately lower than a more rapid discharge like the C20 rating. Do you see the chicanery that could result from misrepresentation of capacity? A 24 amp hour battery at the C20 rating delivers 1.2 amps every hour for a period of 20 hours, whereas a 24 amp hour battery with a C100 rating gets to kick back and only dispense 240 milliamperes for a period of 100 hours. These two ratings are not equivalent. It would be no surprise that the battery with a 24 amp hour C100 rating actually output less energy if you kick the chair out from under it and held it to the same rigorous C20 test. This is to suggest that you must be aware of what standards the battery will be held to for a particular application. A UPS might only briefly require energy to ride out a momentary grid disturbance or initiate an orderly shutdown of an affected system, whereas a battery for a mission-critical off-grid application may have to ride out several days of no sun or no wind before the next recharge. A battery with a nominal energy capacity expressed in terms of the C100 rating gives a false picture of that same battery's capacity when withdrawn more rapidly over the course of 20 hours. Second, a misinterpretation of C ratings stems from the fact that discharge and, as we'll later learn, charge current rates are often expressed as a function of the rated capacity. A battery with a C20 rated nominal capacity can be discharged at the 0.02 C20, 0.05 C20, 0.1 C20, 0.2 C20, 0.5 C20, 1 C20, 2 C20, or any other combination of rates. For example, a battery with a nominal 24 amp hour capacity determined using the C20 rating could be discharged at the following rates. 0.02 C20 would be 480 milliamperes. 0.05 C20 would be 1.2 amps. 0.1 C20 would be 2.4 amps. 0.2 C20 would be 4.8 amps. 0.5 C20 would be 12 amps. 1 C20 would be 24 amps, and 2 C20 would be a whopping 48 amps. Key to your correct interpretation of the C ratings are these two figures right here, 0.05 C20 and 1 C20. A battery with a nominal 24 amp hour capacity at the C20 rating will not output 24 amps for 1 full hour because the nominal 24 amp hour capacity has been expressed at the C20 rating for a period of 20 hours. It shouldn't be a surprise then that the battery would last less than 1 hour if you were drawing 24 amps. Additionally, it should be self-evident that a battery with 24 amp hour capacity at the C20 rating cannot produce 24 amps for 20 hours, otherwise it would have a 480 amp hour rating. That's not what the nominal capacity at C20 means. The only way you're ever going to get 24 amp hours out of this battery is when you discharge it over a period of 20 hours. This means at the 0.05 C20 rate, where 0.05 is 1 over 20. 1.2 amps times 20 hours equals 24 amp hours. Any electrical load drawing more than 1.2 amps will deplete the battery faster and will most likely deliver less than 24 amp hours of energy. Any electrical load drawing less than 1.2 amps might actually see the battery last longer and deliver slightly more than 24 amp hours of energy. It makes sense. You'll last longer performing a leisurely stroll than you will at a dead sprint. Additionally, this assumes the battery is reasonably fresh and operating inside a predetermined temperature range. We'll discuss condition and temperature effects in a moment. Regarding safe maximum discharge rates, C ratings are additionally often used to express how much current a battery can safely deliver. In this sense, the C rating is again a function of the nominal capacity. For example, a 1,800 milliamp hour nominal capacity battery that can be safely discharged at 4 times the C rating can deliver a burst of 7.2 amps of current, whereas one that's capable of delivering 8 times the C rating can safely deliver a burst of 14.4 amps without damage. Again, with your understanding of the inverse relationship of battery demand and supply, one can be reasonably certain that batteries, regardless of the magnitude of the safe discharge, will deplete themselves significantly faster and deliver significantly less energy than the nominal 1,800 milliamp hours when discharged at such high rates. In this case, the C rating is meant to be an expression of a battery's maximum safe discharge current. Consider a 12-volt, 7 amp hour battery where capacity has been determined using the C20 rating discharged at the following rates. 0.02 C20 would be 140 milliamperes, 0.05 C20 would be 350 milliamperes, 0.1 C20 would be 700 milliamperes, 0.2 C20 would be 1.4 amps, 0.5 C20 would be 3.5 amps, 1 C20 would be 7 amps, and 2 C20 would be a whopping 14 amps. Only at the 0.05 C20, where 0.05 is 1 over 20 of 350 milliamperes, would we expect a reasonably fresh battery operated inside its predetermined temperature range to last approximately 20 hours until it reached a predetermined cutoff voltage. In this case, let's say the manufacturer recommends the cutoff voltage at the 0.05 C20 discharge rate to be 1.7 volts PC, where PC means per cell. Therefore, this 6-cell battery's cutoff voltage is 10.2 volts. In a perfect world, the voltage would start out as a flat 12 volts and stay that way. However, a fully charged nominal 12-volt battery would ordinarily start around 12.8 volts, dip down, level out for a bit, then dip down again as it reached the limits of its capacity, and the chemical reactions ground to a halt until the battery reached the predetermined cutoff voltage of 10.2 volts. Again, this is kind of the logic behind the amp hour rating. It ignores voltage variation and assumes a nominal voltage. We started high at 12.8 volts and finished low at 10.2 volts. A nominal value of 12 volts is kind of in between these values, and the battery can be approximated to have a capacity of 12 volts times 7 amp hours, or 84 watt hours of energy. Again, the watt hour is a unit of energy. It is a unit of power, the watt, times a unit of time, the hour. Energy is power times time. This could be converted to units of joules, where 1 watt hour is equal to 3.6 kilojoules, and 1 kilowatt hour of energy is equal to 3.6 megajoules. However, this isn't ordinarily the practice because joules are tiny, annoying, unwieldy units. Given energy is power times time, a true, more accurate representation of energy delivered over the course of a 20-hour period is in actuality the area under the power curve, or for those well-versed in calculus, the integral of the power curve. Given this is a constant current test, one would expect the power curve to exactly match the voltage curve. If we assume an average working voltage of 12 volts times our constant current draw of 350 milliamperes, this means this is an average power dissipation of 4.2 watts. If energy is power times time, 4.2 watts over a period of 20 hours yields our anticipated energy delivery of 84 watt-hours. Again, a true, more accurate representation of energy delivered over the course of this 20-hour period is in actuality the area under the power curve. The nominal voltage and nominal capacity of the battery is basically a rectangular approximation of the energy content of the battery. And if you're reasonably spatially aware, you should realize it's not that far from the truth. The approximated rectangle is including energy content that isn't delivered at the end of the discharge period, however, neglects to account for energy content that is delivered at the beginning of the discharge period. If you take your scissors out and cut off the top left and stick it on the far right side, you essentially get the rectangular approximation. Energy equals a quantity of power delivered over a period of time. 4.2 watts times 20 hours is 84 watt-hours. This capacity analysis, however, is only true for that specific discharge rate. If we discharged it at a greater rate, let's say at the 0.5 C20 value or 3.5 amps, we would expect the working voltage to be less because of the increased voltage drop across the internal resistance. Additionally, a manufacturer may recommend a different cutoff voltage of 9.8 volts at the 0.5 C20 discharge rate. The decreased working voltage would proportionally decrease the power curve, and the different cutoff voltage changes the playing field. At the 1 C20 discharge rate, or 7 amps, we would again expect the working voltage to be less because of the increased voltage drop across the internal resistance. Additionally, a manufacturer may recommend a different cutoff voltage of 9.5 volts at the 1 C20 discharge rate. The decreased working voltage would proportionally decrease our power curve, and the different cutoff voltage changes the playing field yet again. At the 2 C20 discharge rate, or 14 amps, we would again expect the working voltage to be less because of the increased voltage drop across the internal resistance. Additionally, the manufacturer may recommend a different cutoff voltage of 8.7 volts at the 2 C20 discharge rate. The decreased working voltage would proportionally decrease our power curve, and the different cutoff voltage changes the playing field yet again. What successive analysis yields is a collection of discharge curves for varying discharge rates. Each increased discharge rate yields reduced working voltage and possibly a different cutoff voltage. You'll notice the different manufacturer recommended cutoff voltages represent the downturn of the knee just before it rolls off the cliff. This ensures a reasonable quantity of energy is extracted from the battery, yet the battery isn't placed at risk of being permanently damaged. Consider these experimentally observed voltage values for a 12-volt, 7-amp-hour battery where capacity has been determined using the C20 rating discharged at the increased 0.5 C20 rate, or 3.5 amps. Notice the working voltage isn't 12 volts, but rather averages out at, let's say, 11.6-ish volts. Given that this is a constant current test at 3.5 amps, the power curve perfectly matches the voltage curve. One could approximate this as a relatively constant power delivery of, let's say, 40-ish watts. Energy is power times time. Every second the battery delivers power, the energy delivered increases. Power is instantaneous in nature, whereas energy is cumulative. When the battery finally reaches the manufacturer recommended cutoff voltage of 9.8 volts over the course of 63 minutes, close to an hour, it has delivered a total amount of only 42.7 watt-hours of energy. This is substantially less than the nominal value of 7 amp-hours at 12 volts or 84 watt-hours of energy, but to be entirely expected. In this case, we were only capable of extracting around 50.8% of the available energy because at such high discharge rates, we weren't using it efficiently. Consider these experimentally observed voltage values for a 12-volt, 7-amp-hour battery where capacity has been determined using the C20 rating, discharged at the 1 C20 rate, or 7 amps. Notice the working voltage isn't 12 volts, but rather averages out at, let's say, 11.3 volts. Given this is a constant current test at 7 amps, the power curve perfectly matches the voltage curve. One could approximate this as a relatively constant power delivery of, let's say, 80 watts. Energy is power times time. Every second this battery delivers power, the energy delivered increases. Power is instantaneous in nature, whereas energy is cumulative. When the battery finally reaches the manufacturer recommended cutoff voltage of 9.5 volts over the course of 26 minutes, it has delivered a total amount of only 34.4 watt-hours of energy. This is less than the 42.7 watt-hours of energy we obtained during the 0.5 C20 test and substantially less than the nominal value of 7 amp-hours at 12 volts or 84 watt-hours of energy, but to be entirely expected. In this case, we were only capable of extracting around 40.9% of the available energy because at such high discharge rates, we weren't using it efficiently. Finally, consider these experimental voltage values for a 12-volt, 7-amp-hour battery where capacity has been determined using the C20 rating, discharged at the 2 C20 rate, or a pretty high 14 amps. Notice the working voltage isn't 12 volts, but rather averages out at, let's say, a comparatively low 10.7 volts. Given this is a constant current test at 14 amps, the power curve perfectly matches the voltage curve. One could approximate this as a relatively constant power delivery of, let's say, 150-ish watts. Energy is power times time. Every second the battery delivers power, the energy delivered increases. Power is instantaneous in nature, whereas energy is cumulative. When the battery finally reaches the manufacturer recommended cutoff voltage of 8.7 volts, over the course of only 12 minutes, it has delivered a total amount of only 28.9 watt-hours of energy. This is less than the 34.4 watts we obtained during the 1 C20 test, less than the 42.7 watt-hours we obtained during the 0.5 C20 test, and substantially less than the nominal value of 7 amp-hours at 12 volts, or 84 watt-hours of energy, but to be entirely expected. In this case, we were only capable of extracting around 34.4% of the available energy because at such high discharge rates, we weren't using it efficiently. When you place the 0.5 C20, 1 C20, and 2 C20 discharge curves on the same graph, note the differences. Not only do increased discharge rates decrease the working voltage, increased discharge rates also exhaust the battery quicker. If power is voltage times current, power will suffer because working voltage decreases. If energy is power times time, energy suffers a double whammy because not only is power decreased, time is shorter. This goes to show you that the nominal capacity of a battery is a moving target, and the amount of energy capable of being extracted from a battery is a function of how rapidly the chosen application discharges it. Be aware the power curves for these 3 different discharge rates for the same battery will be slightly different than the voltage curves when placed on the same graph. Each discharge rate represents a different current, and instantaneous power will increase with instantaneous current draw. With each power curve on the same level playing field, it is noted that although the battery is delivering more instantaneous power at the 2 C20 rate, it doesn't last long. Again, energy is power times time and can be approximated as the area under the curve. The 2 C20 power curve, although tall, isn't really that wide and represents less area at 28.9 watt-hours than the comparatively shorter but much wider 0.5 C20 curve at 42.7 watt-hours. Other factors affect capacity of a battery, principally battery condition and temperature. As mentioned in the Introduction to Batteries lecture, each full discharge of a battery places strain on it and permanently robs it of a portion of its capacity. Batteries nearing the end of their lifespan show a marked decrease in capacity. Consider 3 different 12-volt, 7 amp hour batteries of varying age. Battery A is relatively new. Battery B is past retirement age, and Battery C has both feet in the grave after suffering a lifetime of heavy use, abuse, and neglect. Again, Battery C is a manky old goat that's been fed nothing but the bitterest of acorns its whole life and then cooked too long. When held to the same constant current discharge rate of 0.5 C20, or 3.5 amps, Battery C exhibits less working voltage at around 10.5 volts and just up and dies 15 minutes into the race. Battery B fares a little better and exhibits an average working voltage of around 10.7-ish volts, then calls it quits at 31 minutes. Battery A, in contrast, keeps its working voltage comparatively high at around 11.6-ish volts, and does so for just a little bit more than an hour at 63 minutes. Given this is a constant current test, the power curves for the 3 different batteries being held to the same current standard exactly match the voltage curves. Power is an instantaneous value, whereas energy is cumulative in nature. Energy is power times time. Battery C delivers less instantaneous power and calls it quits early and delivers less energy. Battery B delivers slightly more instantaneous power, lasts a little bit longer, and delivers a little bit more energy. Battery A delivers more instantaneous power longer and delivers more energy. When all 3 batteries call it quits, having reached their manufacturer's recommended cutoff voltage of 9.8 volts for the 0.5 C20 discharge rate, Battery C delivered only 9.1 watt-hours of energy, Battery B delivered double that at 18.8 watt-hours, and Battery A delivered slightly more than double that at 42.7 watt-hours. This variance shouldn't come as a surprise. A virile and eager young battery can deliver a lot more energy than a tough old goat. Temperature could also affect battery capacity. As temperature decreases from a predetermined reference value, the chemical reactions decrease in mobility and battery capacity proportionally decreases. A fresh battery can be expected to exhibit nearly 100% capacity at the specified predetermined temperature, let's say 20 degrees Celsius, at a specified discharge rate, let's say 0.05 C20. However, it might decrease to only 80% capacity when the temperature is 25 degrees Celsius below the reference point or negative 5 degrees Celsius. It's interesting to note that on the other side of the curve above the predetermined reference temperature seems to suggest that one could get more than 100% capacity out of the battery. This is true to a point, since increased temperature generally increases the rate of chemical reactions central to a battery. This does, however, have its limits though, and battery capacity levels out. Temperatures above a certain point can do more harm than good. Closing out this discussion on battery discharge characteristics, one might also see manufacturer datasheets that incorporate graphs illustrating percent capacity at various discharge rates separately or in combination with temperature effects. The graph on the bottom is meant to illustrate what a battery is discharged at the 0.05 C20 rate. The battery will have 100% of its nominal capacity, as one might expect. However, as discharge rate is increased, available capacity decreases. We observed only 50.8% capacity at the 0.5 C20 discharge rate, 40.9% capacity at the 1 C20 rate, and only 34.4% capacity at the 2 C20 rate from our previous experiment. Other observations can fill out the graph and a curve can be approximated. This allows a user to quickly estimate the effects of discharge rate on capacity. The top graph, in combination with temperature and effect, tells 2 stories at once. Not only does temperature affect capacity, discharge rate also does so, and by tracing the appropriate discharge curve, one can estimate capacity at the appropriate temperature. In conclusion, this lecture discussed battery discharge characteristics. We introduced internal resistance and determined its effect on voltage regulation for various discharge rates, as well as discussed how varying discharge rates, battery condition, and battery temperature affect capacity. The nominal values of a battery are single snapshots of moving targets, and one must be aware of battery chemistry, manufacturer's recommendations, and specific application requirements if one is to estimate capacity accurately. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.